Hi, my name is Bahadur Akhmedov. In this video lecture, we are going to discuss about properties of determinants. Well, first of all, define what is a determinant. Then we're going to talk about 11 properties of determinants. We're going to build all of these properties on the top of each other so that we will try to discuss them, prove them, so that at the end of this lecture, you will feel what is a determinant. And this is going to be a good start to learn how to find the determinant of the matrix and how to use this in its applications. So first of all, let's define what is a determinant. So a determinant is some numerical value which describes the matrix, which is just a property of a matrix, and it works only for the square matrices. So a determinant exists only for the square matrices. For example, we can use the determinant in order to figure out invertibility of the matrix. So if the determinant of the matrix is equal to the zero, then the matrix is not invertible. We can use determinants in order to find the inverse if the determinant is not equal to zero, or we can use the determinants in order to find so-called eigenvalues of the matrix, which are going to tell us the most important values of matrices. So before we talk about the 11 properties of the matrices, I would like to give you a small formula of the matrix, which is the 2 by 2 matrix, how to find its determinant. So we are going to prove this formula later on using the properties, which we're going to discuss. But I would like to give you this formula in the beginning so that we are going to use this in order to just justify a couple of properties, or I will give you an examples of the properties using this formula. So essentially, if you're given a matrix, which is 2 by 2 matrix, we're going to define the determinant using the two vertical lines around the matrix. So if you remember, the matrices are defined using the brackets. So you can't really define the matrix as a vertical lines because the vertical line is the notation of the determinant. So the determinant of this matrix is going to be equal to the multiplication of the entries on the two diagonals, on the main diagonal and on the second diagonal. Then we just need to subtract them. So essentially, it's going to be AD minus BC. So you see, you've got a matrix which is 2 by 2, 3 by 3, 4 by 4, it doesn't matter. Determinant is always going to be a scalar, 1 by 1 matrix, or just a number. So that's why whenever you denote a matrix with the vertical lines around this, it is not a matrix anymore. It's just a number. So let's do an example. So let's say you are given a matrix with the entries 1, 2, 3, 4. So we're going to use this matrix a lot in this lecture. So in order to find the determinant, we need to multiply the entries on its diagonal. So 1, 4 is going to be multiplied together. 2, 3 is going to be multiplied together. Then we just need to subtract them. It is going to be equal to the minus 2. So this is how we can calculate determinants using this formula. So now let's talk about the properties. So the property number 1 tells you that the determinant of any identity matrix is equal to 1. So essentially, if you're given 2 by 2 identity matrix or 3 by 3 identity matrix, so you see I'm going to write down the determinant and put the matrix here. It's going to be 1, 0, 0, 1, and this is equal to the 0, it appears. So in terms of the notation, so this notation is equivalent to this one, 0, 1, 0, 0, 1, and this is equal to the 1 again. So either you put the matrix with the brackets and put the word determinant, that, before that matrix in order to denote the determinant. Either you just put the two vertical lines around your matrix. So the number 2 property tells you that, hey, if the matrix B is obtained from the matrix A by interchanging any two of the rows, then the determinants of the two matrices are essentially going to be the same and their absolute values, but the sign is only going to be changed. So for example, so let's do an example. So if you remember, I've got this matrix A with the components 1, 2, 3, 4, right? And we say that, hey, the determinant of this matrix is going to be the multiplication of its diagonal entries. It's going to be 4 minus 6, which is equal to the minus 2. So now, if I would just interchange the two rows of this matrix, then I would get another matrix. So 3, 4, 1, and 2, right? Now, if you just calculate its determinant by just multiplying its two diagonals, what you get here is 3 times 2, which is 6, minus 1 times 4, which is 4, is equal to the 2. So you see, so these numbers are the same in the absolute value, only the sign is different. So well, if you are given a huge matrix, 5 by 5 matrix, so it doesn't mean that you need to change all of the rows, right? So the first row interchanged with the last one, for example, is only going to change the sign of the determinant. But please note that if you change the two rows, it makes your determinant to be multiplied as a -1. But if you change another two rows, it becomes again the same. So essentially, if I would just interchange the rows of this matrix again one more time, I would get this matrix, and the determinant of this matrix is going to be equal to the +2 again. So essentially, this row also depends on the number of the interchanges. So odd number of the interchanges makes your determinant negative to the determinant of the original matrix, and the even number of the permutations is going to make your determinant the same. So it doesn't change the determinant. So it's really important for us to understand how the permutation matrix is going to change, or permutation operation is going to change the determinant, because it appears we can find the determinant using the Gauss-Jordan elimination. So the property number 3 is important. It tells you that, hey, if you multiply one of the rows as a constant, it will be so if you multiply determinant to some constant, it will be just the multiplication of this constant to one of the rows. So essentially, if you've got a determinant now, if you're multiplying this determinant to some constant, then this constant can become inside the determinant. So you can just get this constant and put this inside the determinant, but it doesn't going to go through all of the rows. It will go to one of the rows, either to the first one, to the second, to the third, and so on. So in comparison, in contrast, if you multiply a constant to the matrix, this constant can go inside your matrix, and it's going to be multiplied to all of the rows, right? So you see, so it's again important for us to understand how this elementary row operations work for the determinant. So if you would like to scale one of the rows, it means that you need to multiply the whole row, whole determinant to the constant. So let's do an example in order to try to understand what does this property tells us. This is property number 3. So let's say I've got this matrix again. So I'm going to write down in terms of the determinants, 1, 2, 3, 4, right? If you multiply this to some constant, let's say 3, it tells you that, hey, this is going to be equal to another determinant. This determinant is going to be equal to the 3, 6, 3, 4. Okay, you see, so I'm multiplying this 3 not to all of the rows, only to the first row. Okay, so if you want, I can just make this second row with another color, 3 and 4. So let's check this. So we know the formula finding the 2 by 2 determinants, right? The determinant of this matrix is equal to the -2 multiplied to the 3. It's going to be equal to the -6, right? And the determinant of this matrix is going to be 3 times to the 4, it's 12, minus 3 times to the 6 is 18, which is going to be equal to the -6 as well. So you see again, so if you multiply the 3, it is going to be multiplied to either the first row, either the second row. It can go inside to your matrix. At the same time, so this property is important because we can extract a constant from a particular row of your matrix. So essentially, so I'm going to rewrite this. So sorry. One more time. So let's say you are given this matrix like a 2, 4, 3, 4. What you can do is you can take out 2 from the first row, and you can write this as a 2 times as a 1, 2, 3, 4. It's really important property. Okay, so it tells us that, hey, if all of the entries in one of the rows are multiplied to one constant, you can take out this constant outside the determinant. We're going to use this a lot. So property number 4 is one of the interesting one and the strange ones. It tells you that, hey, if you've got two determinants which are very much similar, they are different only in one of the rows, then you can add them. And if you add them, you are going to just add them through that row only. So if you remember, if you would like to add the two by two matrices, what you need to do is you need to add all of the corresponding entries, right? While for the determinants, you're going to add only a particular row. If these two matrices are similar in one row, for example, if you are given two matrices, which are 4 by 4 matrices, the three rows of the two matrices should be the same. Only difference should be in that row, in one of the rows. Okay, so let's do an example. So let's say I'm given a matrix determinant 1, 2, 3, 4. Okay, plus let's say the second one is going to be 2, 1, 3, 4. Okay, so you see, so these two determinants are different only in the first row. If I would just add them, what I get is it's going to be 3, 3, 3, 4. Right? I'm going to add only that row. You see, so the second row is just copied. I didn't add them. So let's check out whether the answers are correct. Determinant of the first matrix is -2. We've calculated this so many times. Determinant of the second matrix is going to be 8 minus 3, which is going to be equal to the 5. Right? If you add these two numbers, it's going to be equal to the +3. So the determinant of the resulting matrix it should be equal to the +3. So let's check this. So this is going to be equal to the 12 minus 9, which is equal to the +3. Yeah, true. So you see, so it's really strange property, but it helps us a lot to build our next property, which is the property number 5, okay, which tells you that, hey, if one of the rows of your matrix consists of entirely zeros, then determinant is equal to the 0. Okay, and again, so we can try to prove this using one of the properties which we had. I think it was property number 3 when we multiply a constant to the determinant, right? Or we can take out the constant from a particular row. So what I'm going to do is I'm going to take out 0 from the first row. So I'm going to write this, hey, 0 times is it A, B, C, D, right, is exactly equal to this determinant, right? And again, if you remember property number 3, it tells you that, hey, if you multiply a constant to the determinant, you can multiply this constant to one of the rows, right? For example, if you multiply this to the first row, you're going to get exactly this matrix, okay? So no matter what is the determinant of this matrix, 0 times the determinant makes it 0. Okay, so please note we are proving this for the 2 by 2 matrices. So lots of our examples are for the 2 by 2 matrices, but all of these properties work for any dimensional, any high dimensionality matrices as well. So I hope that you're going to catch the ideas of these properties and you can try to prove these properties for the higher dimensionality as well. So let's go to the property number 6. So if any two rows of the A are the same, then determinant is equal to the 0. Okay. Cool. So it's really good property. It tells you that, hey, if you've got two rows, it doesn't matter whether the first and second or the first or the last one, then the determinant is going to be equal to the 0. So let's go through. Can you go through all the previous properties and figure out how we can prove this? Well, I think the second property should help us. If you remember, the second property tells you that, hey, if you interchange the rows, then the determinant is going to be changed, right? So it's going to be multiplied to the -1. So let's say I've got two matrices. So the A matrix contains the two equal rows. And I've got the B matrix from the A matrix by interchanging those two equal rows. Okay, it sounds strange, right? So I've just interchanged the row, theoretically. I've got the matrix B or determinant B. So what does the property number 2 tells me that if I interchange them, then their signs should be different, right? So the determinant of the A should be negative to the determinant of the B. The problem is these two matrices are equal, right? So in terms of the matrices. So this matrix is the same as this matrix. Okay, so what does it mean? This equation is like one constant is equal to the negative of another constant, right? And it works if and only if this constant is equal to the 0. Okay, so we prove this property number 6 using the property number 2, which tells you that, hey, if you interchange the two rows of the matrix, then the sign of the determinant is going to be changed to the negative. Okay, so property number 7. Adding a multiple of a row into the another row doesn't change the determinant. So if you remember, we call this operation as the elimination operation. So this is one of the elementary row operations, right? So you need to try to understand this property as the conservation law of energy of the matrix. So essentially, if you multiply one of the rows as a constant and add the whole thing into another one, the energy is conserved. So energy is still inside your matrix, okay? So essentially, if you've got this matrix A, B, C, D, you multiply the first row to the constant and add this into the second one, then the resulting matrix is going to be like this, but the determinants are the same. Okay, so it's really important for us how the 3 elementary row operations can be implemented, can go through the determinants in order to build up the algorithm of finding the determinant of a general matrix. So let's do an example for this property. So let's say you've got a matrix like a 1, 2, 3, 4. Okay, so what I'm going to do is I'm going to multiply the first row to the -3 and add this to the second row. Okay, so what kind of matrix I will get? So we're talking about the matrices, but I'm putting the determinants right away to calculate, to be able to calculate them later on, right, immediately. So the first row is going to be the same, right? So 1 multiplied to the -3 added to the 3 is going to be 0. 2 times to the -3 is going to be -6 plus 4 is going to be equal to the -2. Okay, so now let's multiply, let's figure out what is the determinant. So the determinant of this matrix is -2, and the determinant of this matrix is going to be equal to the -2 as well, because if you multiply the diagonal entries and subtract them, it's going to be -2. You see, so the elimination doesn't change the determinant. It's really cool because we can use the elimination to find the determinants, right? Okay, so property number 8 is it's a fascinating, amazing property, which tells you that, hey, determinant of a diagonal matrix is equal to the multiplication of its diagonal entries. So if you remember, the diagonal matrix is a matrix whose all of the entries below the diagonal and above the diagonal are equal to the 0. Then determinant is going to be just the multiplication of those entries on the diagonal. Okay, and it means like if one of the entries on the diagonal is equal to the 0, then the determinant of the whole matrix is equal to the 0. So we can try to prove this again using the property number 3, which tells you that, hey, if you multiply a constant to the determinant, it's going to be multiplied to one of the rows. It means that we can take out a constant from a particular row of the matrix. So let's try to prove this for the 2 by 2 case. So let's say I've got this matrix. So you see, so I can take out the D1 from the first row. So I can write it like D1 times is it 1, 0, 0, D2, right? So you see, so if you multiply D1 to all of the entries on the first row, you're going to get exactly this determinant. So now I'm going to take out D2 from the second row. It's going to be D1 times the D2 times the 1, 0, 0, 1, right? So all of this happens because of the property number 3. And now I'm going to use the property number 1, which tells you that, hey, determinant of the identity matrix is equal to the 1, right? So that is why determinant of the whole matrix, diagonal matrix, is going to be equal to the D1 times the D2. So you can prove the determinant of a diagonal matrix for the higher cases in the same way. So for the 3 by 3 case or 4 by 4 case, the proof is going to be the same. So now, property number 9 is about the triangular matrices. So it appears if you've got a triangular matrix, so if you remember, we have 2 types of the triangular matrices, either upper triangular matrix, like this one, or the lower triangular matrix, then the determinant of those matrices are going to be simply the multiplication of the diagonal entries. So you see, so the property number 7, 8, and 9 are giving us some insights about how to find the determinants, right? So it tells us that, hey, if you do the elimination, nothing changes, okay? Then do the elimination and bring your matrix into the upper triangular form, so which is essentially the Gauss algorithm, right? Or Gauss elimination. Then find the determinant by just multiplying the diagonal entries. Well, you may say, hey, so in the Gauss elimination, you can use the permutation, or you can multiply one of the rows as a constant, right? But yeah, so we know how to deal with those problems as well, right? So if during the Gauss elimination, you need to interchange the two rows, it means that you have changed the determinant. But we know how we have changed that determinant. So it means that whenever you find a determinant by just interchanging the rows, at the end, you need to multiply the determinant as a -1. And again, if you are going to multiply one of the determinants, one of the rows, sorry, to the constant, of course, it changes the determinant. But we know how exactly it is going to be changed. So it means that your determinant, whole determinant, have been multiplied to that constant. It means that at the end, we need to divide that constant, the determinant to that constant, in order to find the determinant of the original matrix. So the three properties, 7, 8, and 9, are essentially going to tell us what is the algorithm of finding the determinant. So let's do an example. So let's try to prove this property number 9. So if you're given this kind of matrix, which is the upper triangular matrix, its determinant is equal to the 3 times to the 2. This is what does the property tells us, property 9 tells us. We are going to try to prove this using the property number 8 about the diagonal matrices and property number 7 about the elimination. So what I'm going to do is I'm going to eliminate this 4. So how I can do is I can multiply the second row to the -2 and add this to the first one. So please note that according to the property number 7, it doesn't change the determinant, right? So what I will get here is 3, 0, 0, 2. Okay, so getting the diagonal matrix from the triangular matrix is so easy, right? You can just do the elimination. So please note, if you do the elimination with the matrices, so the matrices are going to be changed. But if you do the elimination using the determinants, it doesn't change the determinant. So the determinant of this diagonal matrix is going to be simply equal to the 3 times the 2. Okay, so now let's talk about the property number 10, which is like really nice property of the determinants. It tells you that, hey, the determinant of a product is the product of the determinants. So essentially, if you're given the multiplication of the two matrices, and if you would like to find the determinant of that multiplication, then just multiply the determinants of each of the matrices. So it has lots of applications and implications in the matrix theory. So let's first of all try to illustrate this in an example. So let's say you've got the two matrices, 1, 2, 3, 4, and now the matrix 2, 0, 0, 4. We can find the determinant of each of these matrices separately, okay? So what we can do is, now let's just multiply them. So let's say we're given the matrices, not the determinants, okay? The matrices. If you would multiply the second matrix as the first one, so since this is diagonal matrix, which is multiplied from the right-hand side part of the matrix, it is going to scale the columns of the first matrix. So essentially, this 2 is going to be multiplied to all of the elements of the first column. So it's going to be 1 and 6 in the first column. And this 4 is going to be multiplied to all of the columns, the second columns of this matrix. It's going to be equal to the 8 and 16. Okay, so this multiplication is going to lead you to this matrix. So this is the matrix again, okay? So now what I can do is I can try to calculate the determinant. So the determinant of this matrix is equal to the -2. The determinant of this matrix is equal to the 8, right? Because we know that it's the diagonal matrix. So now we need to check this equality, right? So the determinant of this matrix is equal to the 2 times to the 16, which is 32, minus 6 times to the 8, which is 48, right? So the 2 minus 48. So on the left-hand side, I've got minus 16. On the right-hand side, I've got minus 16. It is true, right? So this is just an illustration that property 10 works. So we can apply this in lots of, in a range of problems. For example, so we've got this equation that whenever you multiply a matrix to the constant, and then find the determinant, it's going to be simply determinant of the matrix times to this constant in the power of n, where n is the dimension of the matrix. Okay, for example, if you are going to multiply a constant 3 to some 2 by 2 matrix, I'm going to just put 2, it means like a 2 by 2 matrix, okay? So it tells you that, hey, this is going to be 3 in the power of 2 times the determinant of the AT. I think this comes from the property number 3 right immediately, okay? But we can try to prove this using the property number 10 as well. So what I'm going to do is I'm going to write down the determinant of the k times a as the ki, k times the identity, times the an, okay? then this is going to be a determinant of the k times identity times the determinant of the an. And if you remember, whenever you multiply the k, right, to the matrix, all of the rows are going to be multiplied to that constant. Whenever you're multiplying the constant to the matrix. So if you multiply the k to the identity, you can imagine that all of the diagonal entries of the identity matrix becomes k, right, instead of 1. So it's going to be k, 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 k. So since this is the diagonal matrix, its determinant is going to be equal to simply the multiplication of its diagonal entries, which are k's, which are multiplied n times itself. Okay, and if you multiply this determinant of this a, you're going to get the proof of this property. So again, so it is important equation. So this equation is important, and you can prove this using any various properties of the determinants. Okay, so I think the property 10 gives us the elegant proof of this equation. So another amplification and application of the property number 10 is about the inverses of the matrices. So essentially, you can find the determinant of the inverse by just finding the reciprocal of the determinant of the original matrix. And again, so if you remember about the definition of the inverse is that the multiplication should give you the identity, right? I'm going to take the determinant from both of the parts. From the left-hand side part, it's going to be like this. From the right-hand side part, it's going to be like this. And the property number 10 tells you that, hey, this is going to be equal to the determinant of the A times the determinant of the A inverse. And this is equal to the 1 because the property number 1 tells you that the determinant of the identity is equal to the 1. Then from here, you can find this equation, right? So the determinant of the inverse is the reciprocal of the determinant of the original matrix. It's also important to know. And the last property, 11, it's really important because it doubles the strength of all of these 10 properties twice. So it just increases the efficiency of all of these properties. It tells you that, hey, determinant of the transpose of a matrix is equal to the determinant of the original matrix. Okay, so we can write it like this. So let's just try to illustrate this in example. So let's say I've got a matrix A, B, C, D. Okay, we know that its determinant is going to be equal to AD minus BC, right? Okay, so now I'm going to transpose this. Okay, if you remember, transposition means that I'm going to rewrite the rows as the columns. Okay, so for example, the first row is going to be multiplied as the first column, and the second row is going to be multiplied as the second column. And determinant of this matrix is again AD minus BC, the same. Okay, so what does it mean? What does it imply for us? It implies for us that all of the properties which we talk about today, not 10 properties, which work for the rows, are applied to the columns as well. So all of these properties. So essentially, if you interchange the columns, then determinant is going to be multiplied as a minus 1. If one of the columns is equal to the 0, then determinant is equal to the 0. You can multiply one of the columns as a constant and add this into another column. Okay, it doesn't change the determinant. What else? If you have the two equal columns, then determinant is equal to the 0. So essentially, all of these properties which we talk about, the rows, are true for the columns as well because of this property number 11. So here are all of these properties for the determinants. They are really important. I hope that you've got some feelings about the determinants. In our next videos, we're going to try to construct the algorithms on the top of these properties to find the determinant, to use the determinant to find the inverses and the eigenvalues. So I hope that this lecture was useful for you. Thank you very much for your attention.